I will pop open the CNV project and we'll talk about CNV. And we're not going to run much of anything live for CNV. I'll be quite honest that a lot of the functionality here is computationally intensive and takes some time to run. But maybe to begin with, we'll talk about some data types, and I'm going to let a plot start drawing in the background while we're at it. Where's that spreadsheet? So typically with CNV analysis, we expect that you are starting with either log ratio data coming from a SNP GWAS type chip or from an array CGH product like from Agilent or Nimblegen. And the raw data is going to look like this. So instead of having a big spreadsheet full of SNPs, of diallelic genotypes, here instead we have a spreadsheet with, again, rows per sample, but each column is capturing signal intensity at a particular position in the genome. And the data set I'm looking at today is from the Affymetrix 6.0 platform, which has, for copy number, close to 2 million variant or 2 million probes, 2 million marker positions that it's using. And I have about 400 samples here. This is a subset from phase 3 HapMap. But of course, what we're doing with CNV data is we have this linear sequence of intensity measurements, and we're trying to identify where there is some kind of a distortion in the signal, where there's a consistent increase or a consistent decrease that is consistent with a loss or gain of copy number. And here is an example where I have plotted up in this top region the log ratios for a particular sample. You get the idea that as you go down the length of the genome, this is still drawing in the segment line, but as you go down the length of the genome, you have a lot of noise around this baseline around 0. And depending on the platform you're working with, if you have data coming from a CGH platform or a SNP platform and how much redundancy there is in terms of the number of probes per marker, you may have more or less of this noise. But what we're looking for is some kind of consistent decrease or increase. And in this particular sample, we're in a region where we can see it looks like there's a small little deletion poking out here, maybe another one down here. Over here at the left, it's just off the edge of the screen, but it looks like we may have some kind of a copy gain there. But then we have a really big feature here at the end of, looks like we're on chromosome 1. And that's the kind of things that we're looking for, both small and large-scale CNVs. Now, in this lower plot, what we're looking at here is the B allele frequency. And I assume that most of you are familiar with B allele frequency, but it's a secondary measure that you can look at for assessing copy number. The easiest way to think about this is that as you go down the genome, if you have a point that's down here close to 0 or up close to 1, that means that the SNP genotype at the corresponding position is probably homozygous. If you have a point somewhere in the middle, it means the SNP genotype at that position is heterozygous. And as long as you have this consistent pattern of 3 bands, it's telling you probably have 2 copies overall. When you see this kind of a pattern where you have 1, 2, 3, 4 bands, that's usually consistent with having 3 copies of the genome, because you have the AAA genotypes down here at the bottom, BBB genotypes at the top, but then you have the 2 kind of unbalanced heterozygotes in the middle of AAB, ABB, and that's why you see that variable banding pattern. And in terms of the B allele frequency, we with SVS are able to view it and visualize it, use it as a secondary line of evidence for confirming CNV calls, but we don't actually incorporate it in the algorithm. Our segmentation algorithm is designed to be agnostic to input source, and there are some sources that are simply not able to produce a B-allele frequency, and for that reason, we're not using it. Now, what I'd like to do here is just take a step back and talk about how we are doing this work. So we saw the spreadsheet already of what that log ratio data looks like when it comes in. And there are several different QA procedures that are available for this kind of data. The main ones that we focus on most of the time are the derivative log ratio spread, which is an overall measurement of signal to noise ratio. It's the difference in the intensity from one point to the next. Then there's also this wave detection method, and it's based on an algorithm that I believe was written there at CHOP. This is the Sharon-Diskin method. And you can calculate all of those. I think I have some examples here in the project, so you can see what the wave factor output looks like. In this particular project, it's incredibly consistent. These samples came from, like I said, they're HapMap Phase 3, but they were run in-house, I believe, at Affymetrix. Sometimes you will see some really high outliers in this, and what that will correspond to is a pattern we see fairly often in CNV data of almost like a sine wave as you go down the length of the genome. So as we looked at that one sample, looks like I already closed it, but it was pretty flat down the length of the genome, even if it was a bit noisy. Sometimes you see this sort of up and down pattern correlates typically with regional GC content in that area of the genome. But we're able to detect that. There's a method to correct for that, essentially regress it out based on the GC content. Derivative log ratio spread has similar outputs. It's giving you an idea of which samples have the greatest overall noisiness. And again, in this project, the data is all pretty consistent, but occasionally you will see some pretty extreme outliers. And I don't know what just happened here. I told it to make a histogram and it's going really slow. We'll just restart this. So one nice thing about SVS is if you ever do need to have an unexpected shutdown, it always saves your work and it will bring everything back exactly where you left it off. Let's talk about the real nuts and bolts of what we're doing with CNVs, which is the segmentation algorithm. And our segmentation algorithm is based on a proprietary method that has some roots in one of our legacy software products, which was designed for recursive partitioning and data mining activities. And the algorithm is designed to identify all of the potential change points down the length of a chromosome, or you have the option to use a moving window to speed things up a little bit. But it initially tries to fit a model with up to a maximum number of change points, and you can set that here. So up to 20 per 10,000 markers is one of the defaults. And once it fits a model based on this maximum number, it then goes back through and uses a permutation procedure to statistically determine which of those change points are really valid and are likely to represent some kind of real pattern in the copy number data. And again, it's a method that initially was used for general time series analysis, but we found it actually works remarkably well with this kind of sequential data down a chromosome. Another thing to be aware of with it is that if you happen to have a GPU on your computer that is capable of running OpenCL code, it will really speed up the processing for you. On this particular machine, I have kind of a mid-grade GPU that helps out. I've got another machine here in the office with a high-end NVIDIA GPU that really makes a big difference. Now, the other thing to be aware of with our copy number algorithms is that there are two base methods, univariate and multivariate. Univariate is very similar in many regards to other CNV detection algorithms. It considers one sample at a time and attempts to classify the entire length of each sample's genome. Then the multivariate option is something that's really unique, and I'm not aware of any other package that does something quite like it, but it considers all of your samples together simultaneously and looks for any positions where there is consistent evidence of some kind of signal distortion across all samples. And I find that it is one of the most accurate methods out there for clearly defining common copy number changes and getting consistent endpoints on the segment calls. You can imagine as we look back here at this plot that we had up earlier, and this may take a minute to draw. That's unexpected. It shouldn't need to calculate the extents again. Excuse me. But you can imagine as you're looking at that sequence of log ratios that the endpoint of a CNV could vary by one or two markers in either direction, just depending on whether the noise is at a higher or lower level at the end of the segment. And the multivariate is able to line up all of the samples and get a more consistent estimate of where the real endpoint is for that feature. And so if you look at the outputs from each method, we'll start by looking at the output from the univariate. The most basic output is this segment list, where it is attempting to classify the entire length of each sample's genome. And to emphasize this, let's sort by sample. Hang on, something's going kind of slow here. But you can see here with this first sample, on chromosome 1, from this index tells you the first marker to the 9,010th marker. So across that entire length, the average log ratio in there is really close to 0. And then for the next 233 markers, the average log ratio creeps up a little bit. It's about 0.2, and that is getting to the point where it's consistent with maybe having 3 copies. But then for the next 21,000 markers, it's back close to 0 again. Then we have a short little segment of 3 markers where it's negative 1.5, looks like a deletion. And it's back to neutral for 48,000 markers, and there's 33 where it looks like another little deletion. And that's really what you're going to see is this back and forth from neutral to not neutral. And again, usually you expect neutral copy number to be right around 0. And so we're classifying the entire length of each chromosome for each sample. And after we do that, there are some different ways to look at it. Like if you take that segment list and just look at the distribution of all of those segment means, you see the vast majority of segments are neutral. They're very close to 0. But at a lower level, you'll see a cluster here around negative 0.45. It actually moves around depending on your platform and how the normalization was done. We have a cluster that's probably consistent with 1 copy and a cluster that's probably 0 copies, and it has a long tail out here. Then on the high side, it's not quite as clear, but this is probably the area where we have 3 copies and 4, and whether or not we have anything that's really 5 copies here is ambiguous. But what I want to emphasize is that our software really is not designed to calculate the absolute discrete copy number status. We don't assign a value of 0, 1, 2, 3, or 4 copies to every segment. We really classify everything based on that average intensity within the segment. Now, looking at this, you could get the idea that maybe anything below negative 0.2 is probably a deletion, and anything above positive 0.2 is probably a gain. And we do have options that allow you to classify things using that kind of a method. So you can come back to that segment list, and there's a tool in here under output analysis to discretize the segment list. So you could say, I want to use the thresholds of negative 0.2, positive 0.2, and reclassify these as loss neutral gain accordingly. It will let you do that, and you can calculate summary statistics based on that. You can get case control counts for losses and gain segments. But that's not what we're really focused on. What we typically like to do is look at this spreadsheet of what we call the segmentation covariates. And if you look, this has the same dimensions as the input log ratio spreadsheet, but you notice that the values are more consistent. And what we have here is a situation where we've replaced the log ratio that was initially reported with the mean value within the segment that each marker was identified in. So here, this 0.0249, you might recall, was the same value that was the beginning of chromosome 1 for the first sample in the segment list. Here, well, I think this has been sorted differently. Oh, there we are at the top, 0.0249. So it's exactly that same one. What we would have is the first 9,000 columns in that spreadsheet are replaced with that value, and so on through all the other samples. And by having this kind of a spreadsheet, we can start doing other things. For example, we can put it into a heat map, and this will take a few minutes to draw. But if I just pick one chromosome somewhere, maybe take chromosome 10, you can see this mapping across the length of the chromosome, where we can start to get an idea of where there are some consistent patterns of copy number changes. If there are any really large features, they'll stand out here. We can adjust the thresholds down here. Maybe we'll go to, let's see right there, edit this, negative 0.15 and negative 0.2. That should help us filter the deletions to be closer to those thresholds that we saw looking at the histogram. And on the other side, we can do the same thing. 0.15 and edit this to be 0.2. So now we start to get an idea of where there may be some small common CNVs, like right here. It looks like we've got something up and down of a common small copy number gain. But we can also see more rare things, like right here it looks like there's a sample that has a slightly larger gain in one particular gene. It's actually maybe spanning a couple of genes. So we can explore the data like this by focusing on those intensity values rather than trying to classify anything that might turn out to be a bad classification. Here we have a rare deletion popping out, another rare deletion popping out down here. And the reason I'm emphasizing this so much is if you come back and look at these average values within segments, a lot of other algorithms that are out there for classifying copy number changes focus heavily on the expected distribution within each copy number classification. And they'll have some kind of heuristic model that says if the average is negative 0.5 and the maybe compare it to allele frequencies or whatever to try and make a guess, but there's always some uncertainty with most platforms. Some platforms are better than others at really distinguishing the difference here. A lot of it has to do with what kind of normalization methods are used, but we have found that there's a lot of room for error when you try to make an absolute classification. But if you have large sample sizes in a GWAS situation, just focusing on the intensity change will generally still point you in the right direction. And as an example of that, if you come down here to the bottom, I have a spreadsheet where I have merged some phenotype data together with all of those intensity values from the segmentation. So again, this is the normalized where everything's been replaced by its segment mean. You can run different kinds of numeric association tests, or you can run you can run regression tests. And just like we saw with the sequence data, you can group samples here. And so now we have the situation where we've got p-values plotted on the top. We have copy number heat map down here at the bottom. And you can see here where we've got this little peak. It's not immediately obvious. If we zoom in a little, you can see it a little bit better. But it's a situation where we've got a feature that looks like it's a little bit more common deletion in the bottom half of the plot, which is one phenotype group, than the top half, which is the other. And this is the kind of thing that we're trying to find typically with a copy number GWAS. If we zoom out and look around, we may find some other peaks that would be interesting to go take a closer look at. This particular phenotype is completely random. There's nothing too special about it. But let me check something here. I think that's the one we were just looking at. I don't know if we have any other signals worth exploring too much. But one thing that can be fun, because this data is coming from HapMap, I think that I have a population variable, just like we saw with the 1,000 genomes data earlier. With the HapMap data here, we can probably group this and start finding some certain CNVs that are common or rare in one group or another. But maybe the best way to see this is if we go look at the multivariate segmentation results. As I zoom in here, and it looks like this is an example where, oh yeah, we've definitely got something going on here where there's kind of a jagged edge. It's not really certain where this common CNV ends and starts from one sample to the next. And I'm not positive that this one will be detected in the multivariate, but let's just take a look at it. I'm going to copy this region, then swing down here to where I have the multivariate spreadsheet. Give this a second to open. It is really big and kind of a data hog, or a memory hog, excuse me. But I just want to look at that same region in the multivariate, and what we should see is a clean delineation of where the segments start and stop. So now if I put this into the heat map and navigate to that same location, and this will take a moment to draw in. So you can see the difference in the heat map here with the multivariate is that the endpoints are consistent throughout. Instead of having all that jagged edge around there of what's going on, in this case I see it much more cleanly. If I zoom in far enough, I get to the point where I can figure out which is the last marker that's involved, which one's not. Now, I forgot, I'm still getting used to version 8 and how it shows heat maps. It is a little different than what we see in version 7. But the main thing to be aware of, again, with the multivariate is there are no singletons that are going to get called. It's only going to make segment calls where several samples have some kind of a consistent distortion, and everybody gets the exact same segment endpoints throughout the genome. So it's kind of unique. You have to be careful with it, but it's also really interesting. So with that, I think we've covered most of what I wanted to cover for copy number. There are a number of different association tests that we can do beyond just that simple test that I showed you from the univariate segmentation. We can also do tests based on the multivariate. We can do different types of visualizations on the data. And if you take a look on our website at goldenhelix.com, and I should have emphasized this at the beginning, but there is a section on our website that has a lot of tutorials that will give you more information about how some of these features work. And if you go into the CNV quality assurance tutorial or the CNV univariate analysis tutorial, those are both going to have a lot of useful tips and tricks for how to deal with this kind of data.